Wow, what a holiday break it's been. Did you guys catch the new Star Wars? It was like, I'm wearing a stormtrooper shirt. Pew, pew, pew. Female protagonist. Yeah, yeah. We're going home, Chewie.
We're home.
Oh, you get the idea. That movie was so awesome. It allowed me to escape reality and forget all the stuff we learned in this class. You know, like the deltas and the alphas and the omegas and the Wolfpack movies and stuff. Oh yeah, it was a real treat. So what better way to get back into the school spirit than by literally writing and editing this presentation assignment the day before it's due? By now I'm sure you're all fed up with hearing about Star Wars, but come on, look at this nerd running the presentation. Did you seriously not expect something along the lines of galactic warfare to come into play? Unfortunately, the mass spectrometer, which is what this is all about, it's not lobster vibrations or anything, is not the study of plasma swords and Jedi mind tricks, but it is some pretty cool technology that involves light laser type thingies. So, it's just like Star Wars, but instead of lightsabers, it's electrons, and instead of the Force, it's a magnet, and instead of saving the galaxy, we're weighing atoms. Instead of stars, it's one chemical. Mass Star Trometry Wars. Oh no. The mass spectrometer. Sounds like a pretty epic piece of kit, eh? Well, don't get too excited. The mass spectrometer doesn't open a portal to another world or rehydrate dehydrated food in 5 seconds.
Oh boy, Mom. You sure can hydrate a pizza.
What it does is allow for chemists to weigh... Oh, silly me. I meant measure the mass of an atom using electromagnetic currents. It determines the mass through careful, hidden calculations that factor in where the cations end up and how much magnetic force is required for them to land there. The mass spectrometer works a little like this. A sample is placed into an airtight vacuum called the ionizer, where it is beamed by electrons to convert the sample's molecules into ions by knocking off an additional electron and giving the molecule a positive charge. See why it's called the ionizer? Turns molecules into cations? Cool. Moving on. The next section of the mass spectrometer that we can call the analyzer contains a negative electric field and electromagnetic surface. The negative electric field attracts the newly created ions into the analyzer, giving them enough velocity to travel through the electromagnetic band before reaching the third part of the spectrometer called the detector. The detector contains a super-sensitive electron multiplier, which acts as a plate activated by an ion making contact with it, and an amplifier which raises the once insignificant figure to one that reveals significantly measurable data. The detector can determine where electrons land on it, which is an important piece of information for actually reading the mass spectrometer. Measuring data spat out by the mass spectrometer has little correlation with what we've learned in this particular course, so I am both humbly upset and also proud to inform the class that you won't have to recall any tricky equations. That being said, I am deeply pleased to inform a one Tim Godsey that measurements from the mass spectrometer are outputted and only readable in graph form. When we're looking at a graph, we see two variables, the abundance and percentage form on the y-axis and the m over z on the x-axis. Yes, m over z, or as far as we're logically concerned, the mass. Now right away there's already all kinds of questions, so let's go by and address them. What is m over z? Well, it's simple as 3.14159265359. It's mass over charge. The reason we'll just refer to this value as mass is because upon knocking an electron out of our molecule, we created a cation with a charge of 1, and as I hope you know, anything over 1 is just the numerator's value, so we don't always have to worry about the denominator in this case. How does the mass spectrometer already know the mass? All it should know is a location on a plate. Well, that much is true, however the computer already takes into account the amount of magnetic force required to keep the ion from striking the deflector walls, and the location on the plate spitting out a mass for us. Although, it's not like a chemist to skip pointless steps. I hate graphs! Yes, we know. Thank you, Tim. Something you'll notice about this particular graph is that these abundance values match the natural abundance values of the two isotopes of copper. And by something you'll notice, I mean something you now noticed because I pointed it out. This is because, in a given sample of copper, both isotopes may be present, and they will separate accordingly. They do this because each isotope has a different number of neutrons affecting the weight. Since one isotope may weigh a little less than the other, it requires less magnetic force to deflect it farther, and therefore lands in a different spot. Now you may notice that after running the calculation here, the relative atomic mass doesn't exactly match up with your periodic table's result. This happens because we may not have run enough of the sample through the mass spectrometer to get the accurate reading you see on your periodic table. Running the electric field for 1 minute will display a much different result to running it for 30 minutes, since 30 will allow for the sample to lend a more accurate answer as to what the true abundance of each isotope is. So you're probably wondering by this point in the presentation, how does this accurately apply to physics? Or how does it apply at all? Well, let's ask Mr. Death Stare over here on freelanceteacher.com.
Have you guys taken any physics? Yeah? So I don't know if you remember from physics, the magnetic force only affects charged particles. Magnetic force only affects charged particles. Do you remember the formula for magnetic force? QVB sine theta. It only affects particles with a charge.
Oh yeah, I remember this equation. Who could forget F of B equals QVB sine theta? I could never in a million years unless I'd never been taught it. The application of mass spectrometry to physics is a little advanced, especially for us, considering we had 4 test rewrites and 3 extra study days, so I guess I just chose a topic too advanced for the curriculum of an 11U physics class, because the speed of electrons and precise magnetic force doesn't ring a bell. In fact, there's a few concepts we need to understand before we get into it, like potential energy loss and kinetic energy gain in the context of magnetism. Should have gone with the lobster vibrations. What a drag.